So as we're looking at trends on the periodic table and looking at what happens as we move down the columns and across the rows, the first one that we can look at is atomic radius. Now, from math, you already know what the radius of a circle is. You measure from the center of the circle to the outer edge of the circle. The problem with atoms is that it's not so easy to measure that way, right? We've got a nucleus in the center, fine, we do have a definite point, but we have an electron cloud which doesn't have a very definite edge to it. So it'd be very, very difficult to measure on top of the fact that they're extremely tiny. So instead of measuring that way, what they do is they measure between two nuclei from atoms that have bonded together. So they measure from the nucleus of one atom to the nucleus of the other, and then they divide in two. That's how they set up what the atomic radius is. To consider what our trend is as we go down a group, we have to think about what is happening. So remember that everything is in the period that it is in based on which energy level their valence electrons are in, right? So as we move across the table, we keep adding protons and electrons, and then when we reach the end of any row, it's because that energy level is full. So we move down to the next row to get started with the next energy level. And we continue adding to that energy level until we reach the end of the row, and that is a full energy level, and we start again. Okay, that's an important concept because what that means is as we move down every row, what we're talking about is adding on another energy level. So if you're adding energy levels, what do you suppose happens to the size of the atom or the radius of the atom? Well, of course, common sense then would tell us that what's happening as we go down is that the atomic radius is going to increase. We keep adding energy levels. So the reason that our trend is increasing down a group is the addition of extra energy levels. So the other trend would be what is happening as we move from left to right across the table. So again, we have to think about what's happening. Every element that we move over, one at a time, left to right, means the addition of a proton, right? The atomic number is increasing. So we have one more proton. But because our focus here with elements is that they are neutral, that means that for every proton that we add, we're also adding an electron. But because we're looking at things that are all in the same period, the same horizontal row, all of those electrons that are being added to the same energy level, the same valence shell, right? So if we move from sodium to magnesium, we've added another proton in the nucleus, another electron in the third energy level. When we get to aluminum, we've added another proton and another electron in the third energy level. Move to silicon, you've added another proton, you've added another electron in the third energy level, and we keep going. That is so important that we're talking about the same energy level because we already know that opposites tend to attract each other. So every time we add a proton to the nucleus and an electron to the valence shell, there is an increase in the amount of pull. We call that an increase in nuclear attraction. So the fact that those electrons are in the same energy level means that an increase in pull will actually make the atom get smaller. So our trend across the period is for the atomic radius to be decreasing. It's getting gradually smaller as we move from left to right because every proton that is added to the nucleus is also matched with an electron added to the valence shell, and we have an increase in nuclear attraction. So that means that moving left to right, we are going from larger atoms to smaller atoms. So this is something like what our general trend then looks like. As we move down a group, we would be looking at larger and larger atoms because we keep adding energy levels. As we move from left to right across the table, That means that the atoms are getting smaller and smaller and smaller because of that extra attraction. So our arrow here is pointing from the smallest in the upper right-hand corner to the largest in the lower left-hand corner. So low and to the left is larger. Use that alliteration to help you remember. So if you were comparing elements, you should be able to tell me which ones are larger and which ones are smaller just based on position. The one that is farthest down and farthest to the left would represent the largest atoms. The one that is farthest to the right or highest, that would represent atoms that are the smallest.